Hi everybody and welcome to week 2. Thank you everyone for supporting this. I'm finally getting organised now. I've got a little bank of videos that we're making. Hopefully my tripod gets here soon, not the big one that's in the background, but the little baby one for the iPhone. There are 2 videos now to go with last week's, and if I'm being honest, these later weeks and this week especially, I'll probably make 4 or 5 videos, just little snippets explaining quickly the concepts that we talk about. And I'll send out the tutorial questions after this. So they will come out at some point this afternoon. I do have sessions, but I have a little gap in between some of them. So the recording goes up pretty much straight away. I mean, it is YouTube and they are 4K videos, so they are quite large, but they should go up pretty well immediately. I'm gonna have to render them down and make them usable for YouTube anyway. So last week we were all about carbon and sort of introduction to organic chemistry, and now we get into the nitty gritty of things, for lack of a better term. And what we learn in this week carries through the entirety of organic chemistry. It gets more complex, but the same basic principles remain true the entire way through the course, the entire way through year 11 and 12, university. Obviously, the application of the concepts gets a lot more complex and a bit more difficult to understand. But the thing you'll get sick of hearing me say will be the words intermolecular forces. I think anyone that's done organic chem with me for year 11 and 12 or first or second year uni can attest to that. And they really do underpin this entire topic. If you can get a good grasp on those early and what happens when the different kind of intermolecular forces are present, then you will get I want to say get a high grade. You'll understand things better, and the more complicated things will seem easier because you're taking the mystery out of them. But so valency is a tendency of an element to combine. So the group 8 elements have a valency of 0. Well, for all intents and purposes for year 11, 12 and uni chemistry, the group 8 elements have no valency. They do not react. They are noble gases. And this group number denotes the number of electrons in the outer shell, or the number of electrons available for bonding. Group 1 has 1. Group 2 has 2. Group 3 has 3. An important distinction to make at the moment is groups 3 to 12 don't exist. They will if you go into hardcore chemistry, you start looking at the transition metals, but for this, they don't exist. And that's because they have transition states and they do all kinds of weird things. A lot of them are radioactive and unstable. So we're just worried about group 1, 2, and then groups 13, 14, 15, 16, 17, 18. But for the groups over the right-hand side, you just take away the 1. So group 3, group 4, group 5. So group 3 has 3 valence electrons. Group 4 has 4 valence electrons. And that is where carbon sits. Group 5 has 5. That's where nitrogen sits. Group 6 has oxygen, and it has 2 valence electrons. If we look at group 7, we have fluorine, which is the most reactive element, and it has 1. valence electron. It is the halogens, and chlorine is in there as well. So if we look at that from the perspective of valence electrons, in an ionic bond between sodium and chlorine, sodium has 1 valence electron, chlorine has 7. Chlorine will accept 1 electron to fill its outer shell much quicker and simply than it will give away 7 of its valence electrons. So when sodium comes along and says, I need to get rid of 1 to be back at my ground state, or the noble gas configuration, it gives it to chlorine, and then they're both happy. That's an ionic bond. Carbon and hydrogen, they share their bonding pairs of electrons. So that is a covalent bond. So they're the examples from the periodic table that I was going to talk about. So carbon, that's what we're talking about, is in group 4. It has 4 valence shells. Generally, for the purpose of this course, it will create covalent bonds. Create covalent bonds with hydrogen, with nitrogen, sometimes carbon can form bonds with hydrogen and nitrogen, form cyanide, hydrogen cyanide. Okay. Okay, so yeah, carbon forms bonds, generally covalent bonds. It's generally a sharer, it's not so much giving away or completely accepting. So we discussed electronegativity in either the video or the session last week, but it really is the thing that underpins all of the intermolecular forces. And if we look at what this means, is how likely are they to lose or to use those outer shell electrons, the valence electrons, to bond with something else. So fluorine is the most reactive element. It will react with anything. It will create an acid with just about anything you can put it in. There is no, realistically, there's no way to store fluorine. It will react with any skerrick of water or hydrogen left and create hydrofluoric acid and just eat away any kind of container you try to put it into. So what this means in bonding is that the higher the electronegativity, the more likely that element in a compound will hog the electrons. In that compound. So if you have hydrogen and oxygen, oxygen is the most electronegative by what we call a significant amount, so 0.5 or above. The hydrogen will it will hog an extra pair of electrons, creating a polar molecule where the oxygen is negatively charged and the hydrogen is positively charged. So again, this hogging causes this polarity. So negative and positive. So we think of a magnet. a negatively charged end of a magnet will attract the positively charged end of a magnet. Same thing happens here. So again, polar molecule, and I'll do the classic, go to the whiteboard for this one. I think I've explained this in the video, but I will go over it because it's very, very important. So, polar. So we're going to do hydrogen is up here. I'll just stop the sharing so that you can see the whiteboard better. Need to remember to share that. So hydrogen is up here. It has an electronegativity value of 2.2. Oxygen is over here in group 6. And again, don't go and search for a table and say, yeah, no, that was 3.3. I'm pretty sure it's 3.4. But what's important is that the difference is greater than 0.5. If the distance is greater than 0.5, then you will get a polar molecule. So what happens in water? Water is involved in another special kind of bonding as well. Well, let's use an example because it's relatable. So hydrogen, H2O. So if we use our group 1, so hydrogen and oxygen has 8 electrons. So we have oxygen here, hydrogen down here. So these are what we call now, H plus is what we call an unshielded atom. And I'll go through electron shielding later on in this. So H plus, and then we have an extra pair. They will steal the 2 electrons from hydrogen. So you end up with negatively charged and positively charged. So I'm not going to go any deeper than that, just jumping ahead. But a polar molecule like water will end up with all of the electrons around here. Hydrogen is positively charged. Oxygen comes negatively charged. So if another hydrogen came along, another water molecule came along, there would be electrostatic forces between the negative and the positive charge. And that's the basis of water and why water enables us to be here. And I'll go through why water is a bit weird in a bit. Okay, share this again. We'll find a more efficient way of doing this. So the intermolecular forces constantly mixed up with intramolecular forces, which are the bonding of the atoms to make the compound. So there is a bond between sodium and chlorine that is ionic. It is very, very strong. Covalent bonding is slightly less strong, but is still stronger than the intermolecular forces. And they only influence the physical properties like boiling points, melting points, solubility, And again, if you've looked at what we're going to do in this, that's what we're looking at. You get sick of me saying this, but every single step along the way comes all the way back to these intermolecular forces that we're going to go through. Okay. So this is the electrostatic. So they are caused by the negative and the positive charge. And they don't move. So that's the more you know. So, like I just said, keep jumping ahead of myself by one slide. Do not confuse them with intramolecular forces. They are between two molecules, not between two atoms that make up the molecule. So again, I'll go over it again, and I'm sure you'll be sick of it. It relates to everything. And I will take you through each of the intermolecular forces. There are 3 of them for the intents and purposes of this seminar series. We'll concentrate on 3. There's not many outside, but if I go and say there isn't any others, someone will no doubt come and say, well, actually, there's these ones. So there are others, but they're outside the scope of what we're doing. And everything will relate, and I'll always relate it back, because that way it makes a bit more sense. So dispersion force, sometimes called van der Waals forces. There's ever so slight differences between the two. Again, for the intents purposes of this course, they are one and the same. So the electron cloud is all the orbits of the electrons. And there's no way to predict where an electron would be at any given time. I'm sure there's some weird quantum mechanics there, but again, talking about chemistry and what's reasonable here. At some stage, all of the electrons are going to be on one side or another of one atom. So we then get this temporary dipole where we have a negatively charged end of the atom and a positively charged end of another. So I'm pretty sure it's a UK thing to call them van der Waals forces. Or London forces as well as another one. They all differ ever so slightly, but for the intents and purposes of these, they are virtually the same. So, as the number of electrons in a molecule decreases, these forces go up. It's let's look at the next one. Yeah, okay. There we go. I've got it on my phone, but I keep looking down and looking back up and forgetting. So hydrocarbons. Hydrocarbons are our fuels. I'm sure you've heard that. We produce plastics, we produce pharmaceutical drugs, we produce a never-ending. We produce hydrogen for use in green fuel cells from methane, which is a hydrocarbon, which seems a little counterproductive. But they are the backbone of everything we do in organic chemistry. It also plays a big part in biological chemistry. So if you go and do biological chemistry uni, it's really important to have an understanding of organic chemistry. I never understand why it's not a prerequisite. If you understand organic chemistry, then then biochemistry is much simpler. So I'm going to look at these on the whiteboard. So I'll stop sharing the. So hydrocarbons, as the name suggests, made up of hydrogen plus carbon. Hydrocarbon. Very creative, very stereotypically scientific name. Another red pen. So we have carbon in the middle, and we have hydrogen. So because carbon has 4 electrons available for bonding, hydrogen needs to share 1 to be full, carbon needs to share 4. There is our first hydrocarbon. Or CH4, or methane. Methane is something we use as a gas fuel source. It's also a very, very potent greenhouse gas. It's made from, it comes out of cows, it's flatulence as well. So, this is the basic structure. And then, you know, everything is based off this in organic chemistry. Everything. So we have this carbon backbone running this way. And that just gets longer and longer and longer and longer. It can keep going as long as there's enough hydrogen around to cover it. We say there isn't a length limit, but I'm sure there is eventually. So let's say we're looking at van der Waals forces or dispersion forces. So we have 2 ethane molecules. So sorry, 2 methane molecules. Two molecules of methane. And at some point, this hydrogen over here is positively charged, and this side is negatively. This side is positively charged, but that side is negatively charged. And there will be this very slight electrostatic attraction between these two. So things to note, they are non-polar. Just little snippets to remember as we move forward. Hydrocarbons are non-polar. They only have dispersion forces between them. The boiling point of methane, again, is around the minus 190 degrees Celsius. So very, very weak forces. But there's a number of things that influence the strength of the dispersion forces that we're looking at. So if we have, we have straight chain and branch molecules. So straight chain is like this, goes across. We then have another straight chain molecule this way. If we look at the surface area, there's lots of space for these dispersion forces to bind to each other. Not to bind to each other, to attract each other. So you'll have H here, so on and so forth. So the hydrogen on either side, there's lots of contact points for this attraction to occur. So if we have a branched molecule that looks like this, then there's less area for, so there's really only one space, depending on how they line up, for this attraction to occur. Whereas if it was a straight line, there would be significantly more. So straight chain molecules have higher intermolecular forces than branched chains, because there is simply more positive and negative bits that can come close to each other. This is a fleeting attraction. As soon as those electrons move and change side, then immediately that attraction is broken. Right. So, branch chain molecules. So, I mean, don't worry about the name. It's big and scary. But 2,2-dimethylpropane has a boiling point of 10 degrees Celsius. So, it's a branched chain molecule. So, if we were to look at this, like where the access points for attraction are, most of it is covered. It's only around the edges, like here, that you would have the space to put have the space for the attraction to take place. Whereas if we look at something like pentane, 36 degrees Celsius, it's straight chain molecule. The other molecules line up underneath it. The hydrogens can line up together, and you've got 1, 2, 3, 4, 5 times, you get up to 20 places where these bonds can occur. So it might not seem like much, the difference between 10 degrees and 36 degrees, but it's quite significant. So straight chain molecules can line up, lots of contact points. Branch chain, there's not as much potential for those what's the word? Interactions to take place. So dipole. Unequal electron distribution. As I have said a million times now, electronegativity. And there's a significant difference between the electronegativity values. In year 11 and 12, they might, I haven't checked the QCA guidelines for what they give you in an exam, but if they do still give it to you, then the electronegativity difference has to be greater than 0.5. So HCl, hydrochloric acid. So we have dipole at the chlorine end is a negative, and at the hydrogen end is a positive. And again, if we look at where these two molecules sit, hydrogen is in group 1, so it needs 1 electron to fill its outer shell. Sorry, it needs 7, but it needs to lose 1 in real terms. I don't think it does gain 7. Not come across that. Chlorine needs 1. It's in group 7, it needs 1. And hydrogen will share with chlorine to make 1. But it will not share evenly. Chlorine wants the extra electrons. It's negatively charged. Hydrogen is positively charged. So hydrogen, group 1 with an electronegativity of 2.2. Chlorine, 3.2. Again, I've rounded these. And the difference is 0.5, greater than 0.5. So the electronegativity is considered enough for one of those molecules to take the electrons from the other. Electronegativity trend of the periodic table increases from bottom left to top right. Francium, I think, at the bottom left, all the way up to fluorine. And there's an, oh wait, I won't go through them. I think there's enough information I've given you. So hydrogen bonds are the big one of the three. Without, I'm going to start from, so if there's a lone pair of electrons and a hydrogen atom bound directly to the electronegative atom, then you can get a hydrogen bond. So fluorine, oxygen, and nitrogen are the only three that can produce hydrogen bonds. Again, for the scope of this course. So we talk about de-shielding. Okay, I think I'll go through it after this, so I'll go through it now. So the electronegative atom, or oxygen, steals or hogs, permanently borrows the hydrogen's electron, making it H+. And then nitrogen is, so nitrogen, oxygen, or fluorine is negatively charged. So what, I'll talk about electron shielding in the next slide. So hydrogen bond occurs between the positively charged hydrogen and the extra lone pair of electrons on the nitrogen, oxygen, or fluorine. So oxygen has pretty much, but it has them an extremely disproportionate amount of time compared to hydrogen. So hydrogen is just considered to be H+, oxygen is just considered to be O-. And then you have an extremely negative oxygen. It's an O2-. There's 2 extra electrons in that configuration. It then binds to another hydrogen. And then binds that oxygen. It can also bind to another hydrogen, which can bind to another oxygen, which can bind to it, so on and so forth. So they're really the only reason that we are here. If we didn't have hydrogen bonding, or it was ever so slightly different, we wouldn't be here. The water would not exist as we know. So this electron shielding, when you take away hydrogen's atom, stops the nucleus from trying to pull the outer shell electrons in. So immediately the nucleus, the hydrogen, is trying to attract more electrons. So it becomes really reactive, and immediately when it sees oxygen, nitrogen, or fluorine that's in this state, it will immediately try and bind with it. Yeah, so the inner shells stop the outer electrons from being attracted to the nucleus. When you take that away, then the pulling power of the nucleus towards electrons is significantly increased. So I got through this a bit quicker than I thought again. Oops. So the hydrogen bonds, again, without hydrogen bonds, we wouldn't be here. And not just because of water. But if you look at the structure of the double helix of DNA, it's held together with hydrogen bonds. Proteins, in their quaternary structure and their tertiary structure, are held together by disulfide and hydrogen bonds. The greater the amount of hydrogen bonds in a protein, the higher that protein, the higher the temperature that protein can withstand. So you can see here, you have the double backbone and the peptide bonds between, not the peptide bonds, the amino bonds between nucleic acids there then produce a hydrogen bond with the corresponding side. There's a hydrogen on one side and an oxygen on one side, and they come together. So in proteins, they don't tell, but the protein folds in such a way that it will, it will encourage the formation of hydrogen bonds and disulfide bonds. The hydrogen bonds form, again, they produce these alpha helix and beta turns in proteins that give them their shape. So without these bonds, proteins would just be long, thin chains of amino acids. So two amino acid side chains, so the amino and R group on either side, peptide bond and amino acid side chain, and they form between the two peptide bonds to produce the turns. The greater the presence of these hydrogen bonds, the higher the temperatures that protein can withstand. So there's bacteria that can live in the thermal pools, Thermophilus, I think is their genus name, and they can survive at 93 degrees. And their proteins are designed so that they maximize the amount of hydrogen bonding that occurs. So, water. Water, it shouldn't be water. It goes against all of the rules that we speak about. And it has very, very strange properties. So when water freezes, normally when something freezes, any liquid that's frozen, its volume, it gets smaller. We know that if you put a water bottle into the freezer and you take it out, you can't rest the water bottle on the bench anymore. And that's because the space between the molecules increases, and that shouldn't happen. We know that when something is losing energy, everything comes closer together. Water does not follow the same patterns. Things can walk on water. I mean, not a person, well, depending on what you believe. But there are bugs and insects that can walk on water now. Well, not now, we know they can walk on water. And that's because the surface tension of water, because of these hydrogen bonds, is so high. It quite literally creates a net of water molecules. So if you were to jump off a bridge and hit the water, it's like hitting a brick wall. And that's because of this surface tension. And if the surface tension of water was ever so slightly higher or lower, then the boiling points of water would be completely off. I'm not going to quote any exact figures. The boiling point of water would be off. by a long way. And we wouldn't be here. Okay, well, I've got through this quicker than I thought. I'll have to add a bit more content, but I'll upload a few more videos from the collection to make up for it. So intermolecular forces are different to intramolecular forces. As we know, they are weaker than covalent and ionic bonding. They determine the compound's characteristics. So boiling point, solubility, melting point, reactivity are the big ones. So hydrogen bonds are the strongest of the three intermolecular forces, and the hydrogen bonds are the reason we are all here today. And that is everything for this week. There'll be some topics that will take over an hour. So I'm not just going to talk for the sake of it. So I will leave this week. I'll upload a few extra videos, maybe 3 or 4 videos this week to make up for it, but there will be some later on that do take over an hour. So enjoy the shorter videos to begin with, and I'll upload more little ones to make up for it. Thank you for coming and supporting everything we do, and I'll see you guys during the week.